My name is Ben Sargent. I'm from Rochester Institute of Technology, so other side of the state. So I'm a postdoc, and I'm an observational astronomer, and I'll be talking about studies of infrared spectral studies of protoplanetary disks. So first, a bit of background. So when stars form, they form from giant molecular clouds, and so if you get a cloud that's a little overdense, it begins contracting under its own gravity, and if there's any angular momentum, if there's any spin to the cloud, then most of the cloud will collapse to form the star. What's left over that doesn't make it to the star forms a disk of gas and dust, and so it collapses and becomes a protoplanetary disk. And so eventually all of the cloud rains on to the disk, and then after a few million years, our observations are finding the disks seem to dissipate, and this is the stage where planets and all the other solid bodies of planetary systems form. So I'm studying this intermediate stage where you still have the massive disk of gas and dust, and I'm using infrared spectroscopy to study the gaseous component. So in the past maybe 20 or so years, there have been a number of studies at sub-millimeter and millimeter wavelengths studying the molecules in the disks, and they found such things as CN and HCN and formaldehyde. And there are ongoing studies, surveys of these protoplanetary disks looking for these molecules. Also in the same time, there have been infrared studies of the same disks looking at various molecules. So maybe in the 90s, beginning in the 90s, there were these studies looking for things like carbon monoxide and water and so forth. However, it was the launch of the Spitzer Space Telescope about a little over 10 years ago that allowed surveys of large numbers of protoplanetary disks. And then a few years into the mission, we started, there were a number of papers, here's the first one, that began reporting a number of various molecules from the slightly higher resolution setting of the infrared spectrograph on Spitzer, finding things like water and OH, HCN, C2H2, and carbon dioxide. So this resolution, that's wavelength divided by the spectral resolution element. So it's the smallest wavelength detail you can see on the spectrum. So this isn't all that great, 600, but it's the best we can do. So people were studying things with the higher resolution setting. There's also a lower resolution setting, R of 90. So it's very difficult to study gases with such low resolution, but you can still find lines from such gases as HCN and C2H2. This talk focuses on the stuff you can see at short wavelengths with this low resolution setting. There are many more spectra in the low resolution mode than high resolution because it takes either a brighter source or a longer observation time to get a good spectrum at the higher resolution. So we have many more low resolution spectra. So here are sample spectra from a T Tauri star called RW Riga A. So this is a star with a protoplanetary disk around it. The spectrum in blue is of an FU Orionis star called V1057 Cygni. FU Orionis star is a slightly earlier stage when there's much more material in the disk. So the disk is an accretion disk. It's material that's being accreted towards the star. And for FU Orionis stars, it's thought that the disk is much more massive, there's much more accretion going on, and so the heating for those disks, they're heated more from within than without, and so you get absorption features. And so my study focuses on these T Tauri disks, but I'll start with the FU Orionis disk. So all of this spectral structure that you're seeing in this spectrum comes from water vapor at one temperature. That's an 800 Kelvin model that I'm using. That's the orange that fits the spectrum. I'm using also some continuum, but you get all of the structure with just a simple model. So you see this sort of feature here at 6.6 microns and some sort of ripples here at shorter wavelengths. So this is kind of telling for what's going on in the T-Tauri disks. They are systems that have less accretion. They're heated more from without, more by the star, the radiation from the star. And so you get emission from those systems. And here you have the same feature, but it's a mirror image. So it's emission here. So if I just had emission from water vapor in this spectrum, everything else would be the same, and here I would have the dashed line, but that doesn't fit the data. So it appears there's some sort of component, there's something absorbing at those wavelengths. And in this model, I've used formaldehyde, and I get a decent fit to the spectrum. So if I had very high resolution, like perhaps I could get from a ground-based telescope, this is what I would see if all I had were just water vapor over the 5 to 7.5 micron wavelength part of the spectrum. So you can see that this 6.3 microns, which was sort of a minimum here, it's not really absorption, but it's just a lack of emission. You're seeing down close to the continuum at those wavelengths. At other wavelengths, the shorter wavelengths, you see sort of a cluster of lines that get a bit more densely packed and stronger, around 5.7 microns or so. What looked like a 6.6 micron feature is just a whole bunch of strong lines close to 6.6 microns. But we don't have high resolution, we just have the low resolution. So a bit about perhaps what might not be going on. So there are spectra of T-Tauri stars that are completely boring over these wavelengths. They're more or less just sort of continuum, nothing much going on in those spectra. So it would suggest that perhaps it's not an artifact that's responsible, although you can't rule it out, but the fact that you don't see the features in all of these stars suggests it might not be an artifact. Another thing that it probably is not is features from the stellar spectrum, the spectrum of the star itself. Typically, the emission over these wavelengths is like 5 to 30 times that of the star. So whatever spectral structure you'll see over these wavelengths should be drowned out by a lot of emission from the protoplanetary disk. What structure you do see is probably water, at least in the later type cooler stars. Perhaps some solid materials have features over these wavelengths. These are opacity curves of phyllosilicates. So those are silicate dust grains and such that the crystalline structure is that you get the silicon SiO4 tetrahedra that arrange themselves in sheets, and in between the sheets you have various molecules. And so you can get some spectral structure over these wavelengths, but it doesn't seem to match up to the stuff we see in our spectra. So probably not phyllosilicates. It could also be ices. Ices have features over these wavelengths. Here are ice opacity profiles for formaldehyde, formic acid, and water. And although they have features that are close, they're not exactly a good match. And there have been various studies over the past 20 plus years over of ices, potential analogs for the type of ices you might see in around dust grains and big molecular clouds. And again, not a good match to our spectra. What does seem to be a good match, there seem to be different types of spectra. They're the ones that have the 6.6 micron peak with a shorter wavelengths, sort of a minimum at 6.3, and then sort of a upward rise to shorter wavelengths. So the water vapor and emission, like with the spectrum a few slides ago, seems to fit overall fairly well. And then I need to include absorption from something, and for these at least, formaldehyde seems to be a good fit. For others, water vapor and emission, but something different, in this case, formic acid and absorption. This spectrum DF tau seems especially well fit with the formic acid. There are other stars that don't have much, or they have perhaps no water emission discernible. This one has perhaps a little, but they have these stronger absorption bands at the shorter wavelengths, in this case, that are better fit by formaldehyde, and then others with a narrower feature like DF tau that, again, seem to be fit better by formic acid, but very little water. So I'm not going to go through the whole table, but these are models that I've generated to match the spectra. So the main features are that the emitting areas that I need for the water vapor component are on the order of a few astronomical units. 1 astronomical unit is the average Earth-Sun distance. Okay. So a few AU. The typical water temperatures are 600 to 1200 Kelvin, which are fairly consistent with previous studies. The formaldehyde seems to be fairly cool, relatively speaking, so 50 to 500 Kelvin, and the formic acid, it's not well constrained, but also a few hundred Kelvin or so. I'm running short on time, so I'll just summarize the disk. So the idea is that if you looked at a protoplanetary disk edge-on, you're looking at cooler stuff in front of warmer stuff, and you might expect absorption features. But the few disks that have inclination estimates, it doesn't seem like they're all edge-on. One sanity check is to compare the strength of the 6.6 micron feature versus strengths of water vapor lines at 17 microns from the higher resolution spectra, where you have a better grasp on, you can better constrain the water properties. And so the two strengths seem to correlate. So that kind of makes sense. The stronger the water vapor at one wavelength, the stronger it is at the other wavelength. For confirmation, so water vapor has been observed at a number of other wavelengths. Formaldehyde has been observed for one protostar at 3.6 microns in absorption. So that would be a good wavelength to try to confirm the formaldehyde spectra. The formic acid has bands at 9 and 15.5 microns. The latter is only accessible from space-based observatories. Excuse me, while the 9 micron band is probably the best one, as it's well suited for ground-based observing. And I'll leave my conclusion slide. Thank you.
Questions from the audience? And we have to give you a microphone if you can ask a question, by the way.
So is there something that precludes both formaldehyde and formic acid in combination, because they seem to overlap in that spectral region?
Yeah, there's nothing that precludes them. I just tried to keep the models simple.
Do you have any thoughts as to what's going on, as to why you see very cold formaldehyde but fairly hot water in the same source?
So yeah, this was written up recently in a paper, and that was a question the referee asked. So yeah, perhaps the water can survive at. We can see water vapor in spectra of the coolest stars, so 3,000 Kelvin stars, cooler. So it's a hardy molecule, but the formaldehyde is apparently it dissociates at higher temperatures. So perhaps it just dissociates into CO and molecular hydrogen. So it could be an explanation for why it's only cold. You only see cold formaldehyde.
All right, we got to move on so we can keep on time. Thanks, speaker, again.